Greetings to the respected faculty. I am Lasya Mandapati from CSC AI and MLB section. My roll number is 24951A6686, and today I'll be presenting my project titled Chi Square Goodness of Fit Testing in Vibration Response Classification of Rotating Shafts. This project is a part of my complex engineering problem under the Department of CSC AI and ML. The main focus of this work is to use a statistical approach, the chi square test, to analyze vibration data from rotating shafts and classify whether the machine is running normally or if there's a fault such as imbalance or misalignment. Rotating shafts are an essential part of most industrial machines, from motors to turbines to compressors. When these shafts develop faults such as imbalance or misalignment, they produce abnormal vibrations that can eventually lead to mechanical failure. Traditional vibration analysis methods rely heavily on visual or frequency domain interpretation, but they don't always account for random variations in the data. That is where the study comes in. We've tested a chi square goodness of fit test, a statistical method to vibration signals to check whether the observed machine's vibration behavior matches what we expect under normal operating conditions. This provides a clear and quantitative way to identify when a machine starts behaving abnormally. The main problem we're addressing is that existing vibration analysis techniques often depend only on pattern observation. For example, looking at peaks in a frequency spectrum. This can sometimes be misleading because not all deviations are faults and not all faults cause visible peaks. So, there is a need for statistical vibration that can verify whether vibration data follows a predictable distribution. In other words, we want to determine if the vibration pattern is still behaving normally or if it has shifted due to mechanical fault. Using the chi square goodness of fit test allows us to make this distinction based on data and probability rather than the guesswork. The objectives of this project are quite straightforward. First, to apply the chi square test on real vibration data collected from rotating shaft. Second, to classify the data as normal or faulted based on whether the observed frequency distribution fits the expected one. Third, to validate this data by comparing results from normal, imbalanced, and misaligned conditions. And finally, to explore how this approach can support predictive maintenance, where we can detect issues before they cause breakdowns. So, overall, the goal is to bring statistical confidence to vibration fault detection and the rotating machinery. Before explaining the procedure, let's briefly look at the concept behind the chi square test. The chi square test is a goodness of fit test used to compare an observed data set with an expected theoretical distribution. For example, comparing measured vibration amplitudes to normal distribution that represents a healthy machine behavior. The formula we have used here is stated here to the right. Here, OY is the observed frequency and E of I is the expected frequency in each class or bin. The test basically tells us how much our real data deviates from what's expected. A small chi square value means that the machine is healthy. A large value means that there's a fault. The methodology here follows a structured approach. Step 1, data collection. Vibration data were captured using accelerometers attached to the staff rig. Step 2, pre-processing. Signals were filtered to remove noise and divided into amplitude intervals or bins. Step 3, hypothesis formulation. H0 is where the data follows the expected normal distribution, and H1 is where the data does not follow the expected distribution. Next, step 4. The chi-square statistic was computed and compared with a critical value of 5% or 0.05 significance level. And finally, step 5. Based on this comparison, we are able to determine whether the shaft was operating normally or if it shows signs of a fault. The experiment can be carried out using a rotating shaft setup consisting of a motor, bearings, couplings, and adjustable load conditions. An accelerometer sensor is mounted on the bearing housing to measure vibration responses. The system can be tested under three conditions: normal, or also known as healthy, imbalance by adding mass to one side, and misalignment by slightly altering the coupling. Vibration signals are then processed and analyzed using MATLAB and Python, particularly with libraries like NumPy, SciPy, and Matplotlib for statistical computation and visualization. Once the data is collected, the vibration amplitudes are then grouped into discrete classes and calculated both the observed and expected frequencies for each class. The expected frequencies are determined based on a normal distribution, assuming healthy shaft behavior. The chi square statistic is then calculated for each condition and compared to a critical chi square value for the chosen significance level of alpha is equal to 0.05. This step provides a clear numerical basis for the classification. If the calculated chi square was smaller than the critical value, the shaft is healthy. Otherwise, a fault is indicated. The results were clear. You can see in this table here. For the normal condition, the calculated chi square value was 7.4, which is below the critical value of 11.07. This means the vibration data fit the expected distribution and the shaft was healthy. For the imbalance condition, the value was 18.9, exceeding the critical value. So the null hypothesis was rejected. The data no longer matched the expected pattern. Similarly, for misalignment, the value was 15.6, again above the threshold, confirming abnormal behavior. So, the test successfully distinguished normal and faulted conditions using a simple yet powerful statistical approach. These results highlight the real strength of the chi square method. It doesn't just look at peaks or shapes in the vibration spectrum. Instead, it uses probability to determine whether the observed behavior is normal. In the healthy case, the vibration histogram closely matched the bell shaped Gaussian curve, while the faulted cases showed clear deviations with higher amplitude frequencies. What's interesting is that this test caught subtle changes even when the time domain signal looked similar, which shows how sensitive and reliable it can be for early fault detection. The G squared test has several key advantages for real world applications and monitoring. First, it is simple and computationally efficient. It can be easily implemented in real time systems. Second, it provides a clear statistical decision rule, moving subjectivity from the analysis. Third, it helps reduce false alarms caused by random noise or small fluctuations in the vibration data. And finally, it can be integrated with other diagnostic tools and machine learning models, forming a hybrid predictive maintenance framework. In conclusion, this project successfully demonstrated that the chi square goodness of fit test is an effective method for classifying vibration responses of rotating shafts. It provides a statistically reliable quantitative approach for fault diagnosis, helping distinguish between normal and abnormal vibration patterns. In the future, This method can be expanded by combining it with machine learning algorithms to automate decision making and improve prediction accuracy. It can also be applied to other rotating components like bearings or gears and implemented in real time embedded monitoring systems for industrial machines. That brings me to the end of my presentation. Thank you for listening.